When we talk about metabolism, we're really just referring to the making and breaking of molecules inside of like bodies. And in order to make molecules, we have to break down molecules, both for energy to do that making, as well as for the parts to do that making. And so the making, we call that anabolism. Think about like anabolic steroids boosting your muscle mass, but don't actually go and take them. And catabolism, so breaking down molecules. Think of a cat like attacking something. Catabolism, we're breaking things down. There are many sorts of pathways that connect anabolism and catabolism, and often you can take the same pathway multiple ways. And so you go and you look and you see this crazy looking metabolic charts. And even my simplified version of it looks pretty scary sometimes. But really, there's some core principles at the heart of metabolism that if we understand these principles, we can focus on understanding any pathway we come across. We just need to understand things like how do we actually read these charts? And then once we know how to read these charts, we can think about things like how are these reactions being regulated? What concepts do we see in general with regards to these regulations? Which steps are we going to regulate? So these are some of the focus things that we're going to work on, that we're going to learn about, and then you will have the knowledge to apply these whatever situation you find yourself in. So it's going to take time and it'll take lots of lessons to get used to and things like this, but you've got it. This does not have to look scary. I'll tell you myself, I found metabolism really, really intimidating starting out, and now it's one of my favorite topics to teach. So, going back to metabolism, remember that's the making of molecules, anabolism, the breaking of molecules, catabolism. There's also a term called anaplerotic. We'll refer to anaplerotic reactions as reactions that kind of regenerate pathway intermediates. And one of the things when you're talking about metabolism, and you have to get into your head that when we refer to intermediates in regards to metabolism, we're talking about like these individual molecules in these pathways. We're talking about intermediates of pathways, or rather than talking about intermediates of like a reaction itself. And so we can talk about like enzyme reactions and reaction intermediates and transition states and stuff. Those are not the intermediates we're talking about here. When we're talking about intermediates in metabolism, we're referring to things like all of these different individual units in these pathways, all of these different molecules that are listed here, and then converting between those molecules, we're going to have various enzymes that are going to be helping make that process possible. And during those conversions, we're going to have reaction intermediates, but those are not going to be the focus when we're talking about metabolism. Instead, with metabolism, we're going to be focusing more on, when we refer to intermediates, those are going to be the individual molecules in these pathways. Often we're going to refer to these molecules as like metabolites. And so those are basically just metabolic molecules are often kind of like intermediates in various pathways. In later lessons, we're going to take a look at just like parts and pieces of these at a time. So we'll look at like glycolysis and then the other direction, gluconeogenesis. By considering things more in isolation, it allows you to get a better sense of the chemical logic of these pathways and see that then you can apply these to all of these other intersecting pathways. So we'll talk about glycolysis, which is going to be the breakdown of glucose to give you pyruvate, which can then get oxidatively decarboxylized to give you acetyl-CoA, which then can enter the citric acid cycle, which serves as this sort of central hub of metabolism where all of these different pathways are going to intersect. You're going to see a lot of those anaplerotic reactions kind of feeding things in, our starring role of our malate dehydrogenase. Then we'll talk about how one of the main things in the citric acid cycle is to pass off electrons to NAD to give you NADH or to FAD to give you FADH2. These are when you're doing this, you're passing electrons, these oxidation reactions. The NADH, the FADH2 that carry the electrons that you're passing off are then going to go and in the mitochondria, they're going to be able to cash in those electrons for ATP. And so in next lesson, we're going to talk about how we can kind of use ATP as a form of energy currency. And there's a lot of pathways, and you can see that many molecules can actually go multiple ways. It's kind of like a subway system where you can basically get anywhere from anywhere. You can make any molecule from pretty much any other molecule because they're built up of the same atoms, but you might not be able to do it favorably. You might not even have the equipment in that location. So we'll talk about like compartmentalization and how some things only happen in certain tissues or certain parts of cells because that's where the enzymes helping them out are. Even if a reaction can happen in that location, it might not be thermodynamically favorable. And even things that are kind of at least inherently energetically favorable might not be in the current conditions. And so that's going to get us into the topic we're going to focus on today, which is thermodynamic favorability. We're kind of like spontaneity. How favorable is the reaction right now? Not how favorable would it be if I went and looked it up in a table and looked up the standard free energy, which is telling me about kind of like under these artificial conditions where there's these set concentrations. No, in our bodies, we're going to have these varying concentrations. We're going to regulate the concentrations of those different intermediates to skew things in the direction that we want to go. For example, remember our malate dehydrogenase enzyme. It's going to catalyze the malate 2 oxaloacetate direction in the citric acid cycle. But when we study it in vitro, we're going the other direction because that's going to be more favorable in kind of like inherent favorability. But we can drive it forward by pulling away the oxaloacetate. So let's get into this idea of thermodynamic favorability, keeping in mind that we're going to then be applying this concept to these pathways, to this bigger picture, and then you should have the knowledge to understand so much more than you think you could. About this a little intuitively. So let's take a reaction and we'll say it's like a favorable reaction. So basically, if you let it go to equilibrium, you would have more products than reactants. So we take some equation, we go R2P, and basically we're going to say at equilibrium, we basically have P and a little bit of R. And this is going to be equal to like KEQ. So what this is going to be saying is that no matter how much R and P we start with, we're going to end up with them getting to that ratio. So now let's go and we imagine that we start with equal amounts of them. So I'm going to drop the concentrations brackets just for simplicity. But say you start with something like this, which as we'll see is akin to what we're thinking about under standard conditions, where we have equal amounts of products to reactants. In this case, we're going to have less products than we kind of like want, than we would find at equilibrium. And so in order to get to equilibrium, we're going to have to make more products. So over time, that's what we're going to do. We're going to make more products, which are going to take away some reactants. We're going to make more products, which is going to take away more reactants. We're going to make more products and take away more reactants. And then what's going to happen is that we're going to stop. I don't know how to draw a stop sign very well, but basically what's going to happen is that we've reached equilibrium. So basically the conditions that we have, like at any point, we can do that ratio, we can call it Q. And basically what we're saying here is that once our Q equals our KEQ, there's no drive. And so over here, we had strong drive to the right. But then we went to the right. We started making more product until eventually we got to that point where we had enough products that we were at equilibrium. Our ratio of products to reactants was at equilibrium. There was no drive to move. And that's what happens at equilibrium is your Q equals your KEQ. There's no further drive to move. You've reached equilibrium. What if you started with even more reactants? So we started 1-to-1 here, but what if you were to start with something like this? Well, now you would have really strong drive. Now you have further to go before you reach equilibrium. There's more drive to do so. You're going to release more energy along the way. But what if you start with too much product? If you start with too much product compared to reactants, Well, now you're actually going to have a drive to the left. You're going to start losing your products in order to make some more of your reactants. And so basically, it's not a very good, it's very hard to like draw these out. But basically what's going to happen is you're going to lose product, make reactants. And that's true no matter like how favorable it seemed like it was originally. No matter how inherently favorable that reaction might seem, if you start with more of the reactant, more of the products than you would have at equilibrium, well, now you're going to go backwards. And so how do we maintain things in a state where we're going to be going towards that, we're continuously have that drive to go towards equilibrium, we have that drive to move, that means that we, by definition, can't be at equilibrium. So at equilibrium, there's no drive to do anything, but that's only if you're at equilibrium. Now, sometimes if you want a big drive, you want to make sure that things go in one direction. You want to make sure that your ATP is a good fuel source. There are times when you want to be really far from that equilibrium. But a lot of the times you actually want to be close to the equilibrium, but not at it. When you're close to the equilibrium, well, there it's easy to tip the scale in either direction. And well, why is that important? That's important because remember, we have anabolism and catabolism. We need to be able to make molecules and break molecules. And a lot of the times we want to be able to kind of like use the same equipment in order to do this. In cases like glycolysis, for example, a lot of these are shown as these reversible arrows. No, everything is theoretically reversible. Nothing is theoretically irreversible, but some of them have such a negative delta G that we consider them irreversible. And these are going to be the ones that are super duper far from equilibrium. And these are going to be the points that we're going to want to regulate. These are going to be the points that we can do this regulation, the points that we can drive things forward, the kind of like go or no go points, the points of commitment. And we'll talk more and more, lots of more about how those are regulated. But a lot of the time you'll see that these free energy differences aren't that much. And so what's going to happen is basically when you're near that equilibrium, slight changes in the concentration of these things can have a big effect on what direction things go. Because remember, those enzymes can catalyze things in both directions. And so they only let you reach equilibrium faster. And so depending on whether we're a little more towards one or a little more towards the other, the enzyme is going to be able to help speed you up to get there no matter what. And so when we look at some of the like free energy changes, the actual free energy changes for like carbohydrate metabolism, we'll see that a lot of these are actually going to be near equilibrium, but then there are going to be ones that definitely aren't near equilibrium. And we'll come back to this idea when we talk more about these metabolic pathways and we go in detail into glycolysis. But today we're going to focus mainly on how we get a reaction to be really, really favorable so that this ATP is useful for favoring these unfavorable reactions, for driving reactions being far from equilibrium. We're going to keep it so that we have a lot more of those reactants. We want a situation like this. We want a strong drive. We want something where we have things taking us in the direction that we want. But there's kind of a problem. Do you see it? As we go and we make more of that product, well, now we're losing our power to be able to make more of the product. And so if we want to keep things so that we can keep making more, we're going to have to keep feeding the pathway. And so this is a key thing that we're going to see too, is basically we're going to have to keep adding R, and or using P to keep this going. And it turns out that doing this, we're actually able to keep product formation going. But if we're constantly changing things, it might seem like, how do your cells ever like manage if levels are just fluctuating so much? There's like, whoa, we'd like that equilibrium where things are steady, right? But there's an alternative. There's this thing called the steady state, where basically what can happen is that in equilibrium, what we would say was that we had this constant ratio of P over R, only because we had this equals this in terms of we had the rate of which we were going from our reactants to products equal the rate at which we were going from our products to reactants. And therefore, on net, they're not changing. So every time we make a product, we break it down we go the other direction and make more of the reactants. But at steady state, what happens is that basically P over R is able to stay constant because you're constantly replenishing if you take. So for example, if we had this pathway where we had our reactants and we had the products, well, basically, if we want to lower this, well, there's a couple ways. We could either use it or we could kind of ship it out. And we'll see both of these strategies used. And what that's going to do is that's going to bring down the product concentration. You're going to be driven to the right, good old Le Chatelier's. And so by doing this, then what you're able to do is you're kind of able to keep the drive going. But eventually you're going to run out of your reactants. So you need to keep replenishing this. Steady state is able to keep a constant level of a metabolic intermediate despite being away from equilibrium. So what happens by forming, which can be multiple routes, and consuming, which can also be via multiple routes, or otherwise removing those intermediates at equal rates. So you're forming it and you're removing it somehow, basically by using it, by siphoning it off to another pathway, by taking it out of the cell, otherwise removing them at equal rates to the rate at which you are forming it. And this is in contrast to equilibrium, where basically the rates of forming and unforming were equal. So what's this big difference? Well, the big difference is that unlike equilibrium, it allows the concentrations of reactants and products to change and allows them to be in this state where basically you have a fairly constant amount of that intermediate. So you're able to kind of like have some sense of control, but you're also able to stay in that state where you have a drive to move. You have a drive for things to react. You have a drive. And so this steady state concept is going to be really important. And if we have a drive, if we have things out of whack in a way that basically instead of being at equilibrium, we have things away from equilibrium, we have that strong drive to have a reaction happen, well, then we can take reactions that have a very strong favorable drive, things like the hydrolysis of ATP, and we can use the energy from that to couple it to something that has that actually even has like a positive delta G. So basically it's something that's inherently unfavorable. We can actually get it to go. We can give it the energy it needs to get over the barrier. And then kind of once it's gotten over the barrier, then we can siphon it off into other pathways. So we don't even have to worry about it going backwards too much. And so basically we're able to kind of manipulate conditions inside of our cells to make life happen. And so let's give a little more numbers, a little more technical details into how we can think about kind of the inherent favorability as well as the favorability under the current conditions. So before we get started, just a reminder that basically remember that the enzymes, they can only change this activation barrier. They can only change how big that hump is. And so we have that big activation barrier keeping us from breaking down that ATP just like on a whim, which is great because we don't want it just like going off all over the place. Instead, we can use enzymes to kind of do things in a series of reactions that are able to be more possible and that are also then able to be coupled to other reactions. You're able to have more control instead of just being like a tree burning and releasing a ton of energy, which would not be helpful. We want to introduce that. We want to take away that energy like piecewise, and that's what we can do with all these complex pathways of metabolism. Okay, so let's go back and think about how we can talk about inherent favorability. I know I don't really like math, but we're gonna have to do some math and some critical thinking. I want you guys focusing on the concepts. Don't get bogged down in like too much about the actual numbers, but I do want you to be able to do some basic calculations, and we'll do some examples as well as do some examples in class. But for any reaction, so it could be our ATP, it could be anything, basically we have this equation, the KEQ. So remember that this is what we were talking about kind of informally before. And this is going to be like our products over reactants. Tells how you often see it. But it's important to know that basically in the case where you have like some stoichiometric like coefficients and stuff, so if it wasn't a one-to-one relationship, you then have to take those into account when you do the when you're writing this equation. And you also need to remember to multiply and not add if you have multiple reactants and or products. And so we'll look at some examples, but bottom line, you end up with some ratio of products to reactants. And this is telling you if you let things reach equilibrium, you're going to have this ratio. This KEQ is going to be greater than 1 if the products are thermodynamically favorable. So if you have more products than reactants at your equilibrium, your KEQ is going to be greater than 1. But if you have more of your reactants than products at equilibrium, that means that your KEQ is going to be less than 1. So KEQ greater than 1, thermodynamically favored. KEQ less than 1, reactants are favored. So this is not thermodynamically favorable in the forward direction. Okay, and so when we talk about thermodynamic favorability, well, you should be thinking, that rings a bell. Gibbs free energy change, or delta G. So remember that if delta G is positive, the reaction is thermodynamically unfavorable as written. If it's not favorable in the forward direction, well, then it's got to be favorable in the reverse direction. And so if delta G is positive, it's thermodynamically unfavorable in the forward direction, but favorable in the reverse direction. And if delta G is negative, the reaction is thermodynamically favorable in the forward direction, but not in the backwards direction. And if your delta G is 0, the reaction is at equilibrium. And that's what we talked about before. There's like no favorable, it's not favorable either way. There's no drive to do anything. And so I talked about how we want to keep things like away from equilibrium. But some things we do want to be closer to equilibrium so that we can more easily go back and forth. But then there are times when with things like ATP, where we really want to make them away from equilibrium so that we can better basically use that as a source of energy. So we'll talk more about this in a minute. But basically, when you're at equilibrium, you have a delta G of 0. Now, what we typically see is this thing called a delta G naught. And sometimes you'll see delta G naught prime, which we'll talk about in a second. And this is basically a way to tell us about inherent favorability. So as we were talking about, basically, we had that drive to move when we were far from equilibrium and no drive when we were at equilibrium. So how do we give molecules a sort of like measure of how favorable they are if the favorability is going to depend on the concentrations? Well, what we do is we use this thing called the standard free energy change, which basically says that if you start with quote unquote standard conditions, which we'll define in a minute, of reactants and products, where these are going to be equal amounts of reactants and products, how much free energy would you release or would you need in order to reach equilibrium? If your reaction is inherently like unfavorable in the forward direction, that's going to be a positive delta G naught. So basically, this is saying that you're going to have more reactants than products when you reach equilibrium. It's going to be negative if the reaction is inherently favorable, just like we're used to with delta G's being negative and favorable. So basically, you'd have more products than reactants when you reach that equilibrium. And if you have a delta G naught of 0, or delta, then basically your reactants and your products are equally favored, and you'll have equal amounts of them when you reach equilibrium. And so by kind of doing this, we're able to have a way to compare between different conditions and kind of like figure out what direction things might go based on where they are under those standard conditions. Because as we'll see, there's a way we can go between the standard conditions and the actual conditions. But what are these standard conditions? Basically, the standard free energy change, so this is going to be a physical constant of the reaction, is under the chemistry definitions of the standard state, would be all reactants and products at 1 molar concentrations, 1 atmosphere for gases, and a temperature of 298 Kelvin or 25 degrees Celsius. Are these reasonable though? Let's look just about water. What did we say that the concentration of water was? It's like 55 molar. So that's not reasonable. And well, what would the pH be if the concentration of protons was 1 molar? So remember back to our good old pH. pH equals the log of 1 over our proton concentration. And if we're saying that our proton concentration is 1 molar, that would be 1 over 1 equals log of 1 equals 0. Yeah, I'd say that's not very reasonable. So instead, biochemists are like, okay, we'll do like a transformed standard conditions. So basically, this is what you see with delta G prime naught. Sometimes you'll see it written delta G naught prime. This is a standard transform free energy change under the biochemistry definitions of standard state, where we say, okay, the pH is not going to be 0. The pH will be 7. Water concentration is 55.5 molar, and magnesium is 1 millimolar. That being said, we often use these terms like delta G naught and delta G naught prime kind of interchangeably, and I probably will. Just note that there is that difference. But in biochemistry, we're often dealing with that delta G naught prime. Okay, so this actually relates directly to our KEQ. So going back to that KEQ, we can actually think about we can think about delta G naught in terms of our KEQ. So for a reaction that's at equilibrium, we can determine this delta G naught equals minus RT times the natural log of KEQ, where KEQ, remember, that's our concentration of our products over reactants. So R, that's just our gas constant, T, temperature in Kelvin, and then this delta G naught, that's our standard free energy change. And so the same exact thing you'll see with like delta G naught prime under this biochemistry standard conditions. That would just be delta G naught prime here and KEQ prime here. So yeah, just good old physical constants. I'll give you any that you need in order to do calculations. These are some of the key ones. Bottom line, if KEQ is greater than 1, well, what's that saying? Remember that that's products over reactants. And we said that if we had more products than reactants over at equilibrium, our reaction was going to be favorable. And so if our reaction is favorable, then what's going to happen is we're going to have a negative delta G, right? And well, if KEQ is less than 1, basically that's saying that we have more reactants than products at equilibrium. So our reaction is unfavorable in the forward direction. And so our delta G naught is positive. And in fact, by putting these numbers, we can see that this relationship is actually exponential. And so if you have for a small change in the delta G, you get a big change in your KEQ. So basically at 0 to 2 kilocalories per 0 kilocalories per mole. Basically, remember that's our equilibrium. That's our KEQ is 1. Our concentration of products to reactants is 1. If you're around like 0 to 2 kilocalories per mole, basically you have some of each. Once you get to like 2 to 5 kilocalories per mole, you're mostly going to have one or the other. And if you're greater than 5 kilocalories per mole, then once you reach that equilibrium, if you reach that equilibrium, you're going to have almost all of one. So remember that this, basically this, we have a positive delta G, unfavorable. And here we have negative delta G. And this is going to be favorable. And then again, in terms of our KEQ, this is going to say that our products is greater than our reactants. And over here, it would be that our reactants are going to be greater than our products. So we can go back and forth between KEQ and delta G naught prime, or delta G naught. And the value of having these like standard conditions, no matter how like unrealistic they are, is that then we have tables we can go and we can look them up in. And we can say, okay, under these conditions, we know that this will have this standard free energy change. And we'll see how we can do some calculations with this. But those aren't actually the usual conditions. Even taking into account the water and the pH with our biochemistry transform constants and things, they're still not usual. And so we need to account for this in our calculations of delta G. How do we figure out when we were at that state where we were far from equilibrium? How do we figure out, how can we actually calculate the drive to actually go towards equilibrium? We need to basically figure out the actual free energy change, that delta G. So not the delta G naught, not the delta G naught prime, but the actual, just like in this moment, delta G. And so this is going to be, in order to do this, basically we're going to need to we'll still do basically the exact same thing, but here instead of having KEQ, we have the reaction quotient Q. So this is the generic, just like we had like products over reactants for our, for the, for the KEQ. We have the same thing here, except that we call it Q and it's not at equilibrium. So it's just like in this moment, under these conditions, what is the concentration of products over the concentration of reactants? And again, the same caveats about multiplying, not adding, and raising the coefficients if needed. We can put this into our equation and we can write the current free energy in terms of our delta G naught or delta G naught prime and the Q. So we get this equation where delta G equals delta G naught prime or delta G naught plus RT times the natural log of Q. So this Q is also called the mass action ratio, and it's just like you had with equilibrium, except you're not at equilibrium. And because you're not at equilibrium, or I mean, like if you weren't at equilibrium, this would cancel out. But when you're not at equilibrium, then this is going to help you see what your actual drive is. And so to show you that, yes, this is kind of like the exact same equation as we saw before, well, before we had just simplified it. We know we could write delta G in terms of delta H minus T delta S. And this is just a different way that we can basically write delta G. So both of these are ways that we could write delta G. And in terms of this delta G equal to delta G naught plus RT times the natural log of products over reactants, well, we're saying that at equilibrium, products over reactants is equal to our KEQ. And if we're at equilibrium, then delta G is going to be 0. Remember, that's where we have no drive. If we plug 0 in for delta G and we plug KEQ in for our products over reactants, then we get 0 equals delta G naught plus RT line Q. If we rearrange that, we get that that delta G, or then basically we rearrange that, we get that delta G naught equals minus RT line KEQ, which is what we saw before. And then we can further arrange this if we wanted to solve for KEQ, knowing delta G naught. But this is at equilibrium. But now what about at any time? Well, at any time, we can use our mass action ratio Q and plug that in. And now delta G equals delta G naught plus RT times the natural log of Q, which is the same equation we had up here, but we could just simplify it because we knew that we were at equilibrium. And therefore our Q was really our KEQ and our delta G was 0. We can rewrite this formula in various ways. And one of the ones that I find the most helpful is basically delta G equals the minus RT times the natural log of KEQ over Q. And why I like writing it like this is because it shows explicitly how the delta G is related to and dependent on the ratio of your KEQ and Q. So it's not good enough how inherently favorable that reaction is under those standard conditions. We need to know what are the conditions right now, because that's really what's going to drive what something happens. So let's think about how we can make this reaction negative or positive. First off, what do we want? Well, if we want our reaction to go into the forward direction, we're going to want to make this negative. But in order to make this whole right side of the equation negative, basically we're going to have to make this positive. And when you take a natural log of something that's greater than 1, you're going to get a positive number. And if you take a natural log of something that's less than 1, you're going to get a negative number. And so how are we going to get this to be positive? Well, we need our KEQ over Q to be greater than 1. And so if we're saying that our KEQ is greater than Q, what we're saying is that at equilibrium, we would have more products than we have right now. And so we need to go in the forward direction, right? So if KEQ is greater than Q, basically you have a drive to go forward. But what's going to happen is that if your Q is greater than your KEQ, basically that would be saying that you have more of your products currently than you would have at equilibrium. And so you're going to actually go backwards. It would be unfavorable in the forward direction. This would turn out to be negative. A negative times a negative equals a positive, and your delta G would be positive. To summarize, and these are really important points that I want you guys to know, if your Q is greater than KEQ, delta G will be positive and the reaction will be driven towards reactants. If Q is less than KEQ, delta G will be negative, reaction will be driven towards products. If Q equals KEQ, then delta G will be 0, the reaction is at equilibrium, and there's no net change in concentrations of products or reactants. And if they're within 1 to 2 orders of magnitude of each other, the reaction is going to be near equilibrium. We saw how whether you're larger than or greater than 1, your ratio was going to determine whether it was favorable or unfavorable in the forward direction. But that's not enough. We want to know how favorable or how unfavorable. The magnitude of the ratio is going to tell us like the magnitude of how favorable or how unfavorable it is. How much energy would be released from this, or how much energy would we need to make this happen? And so as the ratio of KEQ to Q gets bigger, what that's going to mean is that your reaction gets more favorable. There's more products that you need to kind of make in order to reach that equilibrium. But as that Q gets bigger, well, now that's going to make it more and more, that number more and more negative, which is going to make the side of the equation, the whole equation, more and more positive. So the further you get from equilibrium, the more energy that's needed or given off to get to equilibrium. And therefore, the thermodynamic favorability and molecular usefulness is highly dependent on concentrations. And this means that even if you have a reaction in which the delta G naught prime is actually positive, you can have a situation where your concentrations are so out of whack, your Q is basically so much smaller than your KEQ, that you're able to make this reaction is actually going to be favorable. If you have so much more of your reactants than products, you can kind of overcome that barrier. Because even just if you think about things probabilistically, well, if you have a lot of reactants and not a lot of products, even if they kind of just accidentally change into products, basically, even if it's not very favorable, if it happens, basically it has more chances to happen because you have more of those reactants. And so if you you're far from that equilibrium, you're in terms of your KEQ and your Q, well, now there's going to be basically a stronger drive to move. And that drive to move might be enough to overcome the inherent unfavorability, the inherent fact that at equilibrium, you're still going to end up with having more of your reactants than your products. But we have so much more reactants in the current state that we're still able to transform some of those into products, and that'll still be favorable. How much of a barrier you'd have to make up is going to depend, though, on your delta G naught prime. The bigger positive that would be, the further from equilibrium you would need to be in order to make that reaction actually go. But if that is smaller, then it's easier to go back and forth. And therefore, we can kind of have reactions that have a fairly neutral delta G naught prime. And we can do things in the forward and reverse direction. And we can control which direction things go by controlling those concentrations. And then things that are inherently favorable, well, they also are going to depend on the concentrations. And so this is actually one of the reasons why ATP gets its power. Here's some key takeaways. One is that the standard free energy change, delta G naught, is kind of like telling us about the inherent favorability. So if you were to mix these molecules together, let them reach equilibrium, what would you find more of? The products or the reactants? Well, if a reaction is favorable, you find more of the products, which would mean that you would have a negative delta G. And you would have a KEQ that's going to be greater than 1. But if you have a reaction that's not favorable in the forward direction, you find more reactants than products at equilibrium. Your KEQ is going to be less than 1. The delta G is going to be positive. However, things are not usually at these standard conditions. And so we need to take that into account. We need to figure out the actual free energy change. And for that, we want to figure out delta G. And that is going to depend on the actual concentrations of things at this moment. That's going to depend on our reaction quotient. Products over reactants again, but here we're not at equilibrium. And because we're not at equilibrium, we have the drive to move towards equilibrium. And so it's this difference between the Q and the KEQ, between whether we have more products than we want at equilibrium or whether we don't have as many products as we want at equilibrium. If we have more of our reactants than products than we would have at equilibrium, we're going to be driven to the right. We're going to make more of those products. But if we're building up our products, well, now what's going to happen is basically we're slowing down that drive. And so if we slow down that drive as we approach equilibrium, we're making it so that our reaction is less useful. And so we have to, if we want to keep even a favorable reaction, if we want to keep it favorable, we're going to have to manipulate the concentrations